Okay, George Dishman has come up with this thought experiment. Here it says, suppose Alice is a flatlander living on the surface of the infinite plane, while Bob is a flatlander living on a surface of the sphere. If they are sufficiently intelligent, both could develop the maths to model 3D manifold containing their multiverse, and both would be aware of the possibility of 2D universes, which are spheres and planes. And when each does the test I outlined, Bob would be able to conclude that he lives in a spherical universe, but Alice could only conclude that her universe was flat to within some error bars as far as she could observe. This relates back to a prior couple of paragraphs that he wrote. I'm sure you know the story of Flatland, written in the 19th century. Consider the case of a flatlander who sets out to investigate the geometry of the universe within which he exists. He takes a reference point and draws a circle of radius r, then walks around it and measures the circumference c. He repeats that for radius 2r, then 3r, and so on, but he finds the ratio is always the same. C over r is a constant. He concludes that his universe is a flat plane and could be infinite. Now instead, suppose he found that as he measured at increasing radii, the circumference increased, but not as quickly. The ratio c over r reduced as r increased. He might realize that the ratio was following a pattern, and that the circumference would eventually reach the maximum and then start falling for increasing radius. While he might not be able to understand or visualize it, he could derive the equation for a sphere. Now what I'd like to do is kind of go through this example in a little bit more detail and just kind of imagine this situation where I'm going to kind of draw this in more dimensions, but we've got this flagpole and this guy is walking around it. And he goes around in a circle like this. Okay, I'm going to go ahead and draw that out. Of course, circumference equals to 2 pi r. Now let's try to picture it on the surface of the sphere. And the sphere is going to have a couple of coordinates. I'm just going to describe this as theta. As he goes around, this distance here will be r sine theta, and the distance around the sphere, this distance here is r theta. Let's see the arc length. If it's in radians, it's r theta, and so the radius from, if he measures out the radius from that flagpole, he's going to find the radius is r theta, and the circumference is going to be 2 pi r sine theta. But he's not going to see these variables. He's not going to see this variable r. He's not going to see this variable r theta. All he's going to see is r and c. And as he goes, he'll find this pattern emerges. Well, one thing that he's going to notice when he does this, oh, well, no, that's going to be natural. He's going to be turning left all the way around. Let's say he's doing this for a while. He doesn't really start doing any measurements right away, but he goes all the way down here and he notices a peculiarity at this spot. He's gone 314 steps that way, and when he gets to here, he's walking around. Well, I don't know how the rope he's holding on to is doing it, but that rope is going all the way around the sphere, and he's walking a very small distance around in the circle, drawing out a little circumference right there. So he notices that strange phenomenon when he gets down to 314. He goes back up, and he comes up to this point of the sphere and says, okay, there's 628 paces around the circle right here. Now, he should be able to conclude from that he lives on a sphere. Well, because there's other phenomena that are indicated, such as when he drags this rope around, He walks around in a circle here, and a small circle here, and the rope pulls her all the way around the circle. And so there are all kinds of ways to confirm that you live on a sphere, if you really do live on a sphere. But let's just collect a small amount of data up at the top. Let's say his rope isn't quite long enough to get all to reach very much past this point, maybe not even to that point. Let's see what happens. So I'm thinking along the lines of coming up with a radius and a circumference, and then maybe what would be the expected circumference with that radius and the expected radius with that circumference. Okay, so there's some overdetermination here, but we have the rope length at r theta. We have the measured circumference is 2 pi r sine theta. And then based on that, we would expect the radius to be the measured circumference over 2 pi. If we were just given the circumference, this is what we would expect the radius to be. And the expected circumference, if we were just given the radius, wait, and the radius, if we were just given the rope length, if we were just given the rope length r theta, this is what we would expect the, let's just write that, rope length theta. This is what we would expect the rope length to be. I mean, the circumference to be. Okay, so now given that, I'm not entirely sure what I want out of that, but I want some kind of data table, I think. And here's a reasonable graph. Rope length of theta, comma, expected circumference would be the blue. And then it turns out that the measured circumference is less than the rope length. Now then, how would this guy explain the difference between the expected and measured circumference? So this is one of the graphs. I should make another one though that has the other possibility. This one shows a difference between the expected circumference and the measured circumference, but it trusts the rope length. Now here's another version of the graph where the measured circumference is trusted, but the rope length is not trusted. But there's something definitely wrong with that because that should not be a straight line. Expected radius is supposed to be measured circumference over 2 pi. Expected measured circumference. Oh wait, no, that would be a straight line, wouldn't it? 2 pi r sine theta and 2 pi. Oh, yeah. Yeah, because we expect it to be a straight line. Okay, that's fine. So if we just had this data, then a possible conclusion that you might draw is that you are living on a sphere. And that conclusion, if you did draw that one, you would expect to find other indications that you were living on a sphere, such as maybe if you walked continually in a straight line for far enough, you will eventually come back to the same point in the space. However, let's discuss a couple of other possible things that you might think. One is that you might think that being further away from the center causes your measured circumference to be off from your expected circumference. For some reason, your footsteps, maybe what you would think is that for some reason when you're out here far away from the center, your footsteps become elongated. And so when your footsteps become elongated, then you measured a smaller number of paces around the circle than you should. Another possibility is that when you move away from the circle, from the center, maybe the rope is somehow the expected radius and the rope length are not staying the same. So somehow the rope is putting out either extra or not as much length as it should. I don't think this one is as good an explanation, and I would probably prefer your paces to be somehow elongated. Let me run through that again one more time, imagining two different observers in two different universes, and, and both are getting the same set of data. Um, and in the first set of data, the both of them get the orange line here. Both of them get, as they extend the rope, the measured circumference is theta. Or they could be two observers in the same universe, drawing different conclusions. And one of them concludes that this is associated with rope length equals r theta, measured circumference equals r, 2 pi r sine theta, and they conclude, I live on a sphere. The other observer sees exact same data, may even agree this does seem to be the relationship, but he might conclude something else. He might conclude that my steps, my rulers, my steps are more invigorated, more energetic at greater distance from the flag. Now, so these are two different hypotheses. One of them concludes that his measurement of the circumference is correct. The other one concludes that his measurement of the circumference was incorrect. So this guy says they are correct, but we live in we are two-dimensional beings in a higher dimensional space. And this guy says, no, we're not two-dimensional beings in a higher dimensional space. We are two-dimensional beings in a flat space with a phenomenon where our measurements become inaccurate at in certain places. So one further thing, just to make this a little bit more, so instead of r theta, whoops, I need to move that back up. Instead of r theta, r 2 pi, let's talk about that in discussion of r theta, let's say, say the rope length is L equals r theta, and then the circumference, we'll say r, we'll multiply by theta over theta, 2 pi sine theta, and then this will be L here. And so that's the circumference is 2 pi L over theta sine theta. So that is the measured, and then the expected would just be 2 pi L, the expected circumference. All right, thanks for watching.